Okay, in this section, we will explore how a simple descent method applies for prime numbers of the form 4k plus 3 with representation x squared plus n times y squared. Before we start, it's worth noting that Brahmagupta's identity, originally employed for numbers expressed as x squared plus y squared, can be extended to accommodate those of the form x squared plus n times y squared. The simple descent method developed in the X section may also be extended for representations x squared plus n times y squared for primes 4k plus 3, when there isn't a quadratic reciprocity between p and n. This enables to obtain an equation m squared plus n equals p times k sub 1 in order to kickstart an infinite descent, which may lead to a representation or just divisibility. A minor modification of Neven's lecture on congruencies of degree 2 prime modulus show that as n is a quadratic non-residue of p, then, given Euler's criterion, we multiply all terms by n. We replace p as 4k plus 3, we simplify, and then we regroup. Finally, we compute the congruence so as to get the smallest integer of the square, which is m. So let's see an example with a relatively big prime number, 13,300,711. We check primes 4k plus 3 for n, up to 3,647. That is, at most the square root of 13,300,711. We first tried with 3 for n. We check Euler's criterion for 3. Then we apply Neven's congruence as seen before. And so we get that 4,242,385 squared plus 3 is divisible by 13,300,711. As we got the initial equation, we can now start the simple descent, as seen in this section 8. Once we got all the squares plus 3, we can then compute the extended Brahmagupta's identity in order to reach the desired solution. In fact, we reached the solution. 13,300,711 can be represented as 2,806 squared plus 3 times 1,345 squared. Thus, we got divisibility plus representation. Later, we'll see that in other values of n, we'll got divisibility but no representation. Next, let's examine the representation as x squared plus 7 times y squared. We'll briefly review this case, so feel free to pause if you need to verify the process. In the end, for n equals 7, we got both divisibility and representation. Now, we check case for n equals 23. Here we have divisibility but no representation. That is, we reach the smallest x squared plus 23 times y squared, that it's divisible by 13,300,711. When we analyze n equals 59, we reach the same conclusion. We got divisibility but no representation. The next case where primes of the form 4k plus 3 satisfy Euler's criterion is when n equals 599. And this time we reach both divisibility and representation. We still need to examine 4 more cases, beginning with 631, that shows both divisibility and representation, 823, which also satisfies both divisibility and representation criteria, 1319, satisfies both divisibility and representation requirements, and 3467, which also satisfies both divisibility and representation criteria. In this table, we summarize the findings. For primes of the form 4k plus 3, where Euler's criterion holds with -1, we consistently observe divisibility. However, in the cases of 23 and 59, representation is lacking. So a question naturally arises. How is it that divisibility does operate, whereas representation in the form x squared plus n times y squared fails to hold? Well, x squared plus n times y squared is just a special case of the general quadratic equation in two variables, x and y. Just as a warm-up, let's first examine the case of the product of two general quadratic equations which have the same coefficients a, b, and c, as well as the same variables x and y. However, they differ in the signs of the second terms. And that's precisely the expression x squared plus n times y squared, where n equals 4 times a times c minus b squared. Notice that minus n refers to the discriminant, a concept familiar from the days of learning quadratic equations in school. Indeed, we can observe how this applies with those couple of values n, such as 23 and 59, that for the prime number 13,300,711, we ascertain divisibility criteria without attaining a suitable representation as x squared plus n times y squared. Keep in mind that these formulas work with just two variables, x and y, yet hinting at the possibility of a broader overarching formula. Dirichlet advances this notion by introducing formulas involving two additional variables, x, y, w, and z. Ultimately, through the application of Lagrange reduction, we uncover a couple of handy formulas applicable to the majority, though not all, cases. So let's now take a look at Dirichlet's version of composition. Here, we still have the same coefficients a, b, and c, but different variables, x and y on one equation and w and z on the other. Through the application of Dirichlet's transformation, we can reshape this quartic equation into a quadratic form. Furthermore, as an extension, we can derive a variation where the second terms of each quadratic equation feature opposite signs. Now it's time to introduce Lagrange reduction. It allows transforming a binary quadratic equation multiplied by a factor into x squared plus n times y squared. With that in mind, we can deduce an analogous reduction for a similar case, when those same coefficients appear but in altered positions within the equation. Thus, we can apply this Lagrange-like reduction to Dirichlet's version of composition and its variation. Applying Lagrange reduction to Dirichlet's formulation of composition yields a couple of handy formulas. These handy formulas address the task for most cases. They reliably yield solutions for integer inputs when b is even, as 4 divides b squared minus 4 times a times c. Moreover, they remain applicable when b is odd, provided that all elements of the set x, y, w, z are odd, or if at least one of the following pairs is even, x and y, w and z, x and w, or y and z. However, the formulas fail to produce solutions when x and z pair is odd, but y and w pair is even, or when x and z pair is even, but y and w pair is odd. Let's examine a few cases to illustrate the concept. Consider the case where n equals 23. Revisiting the infinite descent equations, we verify whether all values can be expressed in the form x squared plus 23 times y squared. As you can see, only 3,205,712 and 4,371 conform to this representation. Obviously, 9 conforms too. This is precisely where the handy formulas prove useful. So here we present 4 additional binary quadratic equations characterized by coefficients a, b, and c, resulting in a discriminant of minus 23. Upon scrutinizing the representation of the 6 given values, we conclude that the form 2 times x squared minus x times y plus 3 times y squared aptly accommodates all cases. Lastly, we apply the handy formula to validate its effectiveness for all equations in the descent. Indeed, it works because all pairs x and w are even. The case with n equals minus 59 follows a similar pattern, albeit with a slight variation. In the first equation, the pair x-w is even, while in the second and third equations of the descent, it's the pair y-z which is even. The scenario with n equals minus 83 exhibits a similar pattern too. The effective representation is the one of the fourth column, as it ensures that the pair xw is even in all equations of the descent. Notably, the representation seen in the last column, where the difference is just a minus sign in the second term, nearly suited, as the pairs xw and yz were all odd for the first, second, and third equations. However, it faltered in the fourth equation, as it was impossible to ensure that all variables were odd or to find a pair of even variables. The last case is n equal minus 107. Here, employing both handy formulas becomes necessary to complete the descent equations. The form of the second column works for the first 5 equations, as all 4 variables are odd at each step. However, for the final equation, we require the form of the third column, same as the second, but with a minus sign in the second term. As all 4 variables, x and y for 13 and w and z for 11, remain odd, it ensures the validity of the second handy formula with integer values. Just a small addition. One other thing to notice, and further investigation is needed, is whenever a number could be represented as x squared plus n times y squared, then almost all other forms were applicable to. See the yellow lines. And assuming, as always, that x and y are positive integers, it fails for the value 60 when n equals minus 59. In fact, it fails too for 24, 60, 84, and 108. Before concluding this section, let's take a closer look at how Helmholtz's convergent solution addresses the equation x squared plus n times y squared, where n is a prime of the form 4k plus 3. These slides demonstrate that Helmholtz's version of the beautiful formula yields solutions for all cases, much like the simple descent plus Nevin's congruence method. However, a minor difference is observed. Helmholtz's beautiful formula does not provide the smallest values for cases n equals 23 and 59. Specifically, Helmholtz's solution gave us a quotient of 13 for n equals 23, while simple descent yields 9. Similarly, for n equals 59, the quotients are 25 and 3, respectively. To end section 10, let's highlight a few key conclusions. A slight adjustment to Nevin's congruence of degree 2 prime modulus enables the initiation of a simple descent, ultimately leading to the discovery of a representation in the form x squared plus n times y squared for primes of the form 4k plus 3. However, it's crucial to note that while divisibility is a certainty, representation is not always guaranteed. We illustrate this with various instances where divisibility occurs, yet representation may or may not occur. To comprehend why divisibility invariably occurs while representation may not, it's instructive to revisit Dirichlet's approach to composing binary quadratic forms with identical coefficients, a, b, and c, and variables x and y. Subsequently, we introduce a couple of handy formulas that employ the same coefficients, a, b, and c, but different variable pairs, x and y, and w and z, which prove applicable in most scenarios. In the next section, we'll explore representation as x squared plus minus n times y squared for primes of the form 4k plus 1.